So this is towers. This is an assignment I ran 2 semesters ago. It took a break last semester. I had to bring it back for this. Semester. I had to change it for the for the current iteration of the course. But it's making a comeback, and we can play towers again. So this is what I call a tower offense game. I don't know if that's a real genre or anything, but I'll invent it if it isn't. So instead of a tower defense game where you're placing towers and fending off hordes of wave after wave of incoming attackers, we're the attackers in this case, and we play it as an MMO. Hey, and we're doing pretty good. Oops. So to get this working takes a lot, possibly all of the concepts of the course, a lot of the homeworks. It's almost like they have aimbot, because they do have aimbot. So aimbot is designed to be part of this assignment. The original aimbot assignment, when I first did that, it was getting these towers to shoot. It still is that, and the GUI for aimbot was one of these towers. And that is how these towers are shooting, is with a genetic algorithm. But this is where that aimbot fits in to a larger game, a larger experience. So it's maze, it's aimbot, it's physics. There's a lot of the course goes into building something like this. And oh man, it's already 101. I thought I was I'm thinking I'm starting so early, just so we can chat and play with this for a little bit. It's already go time. It's 101. And view count is off as usual. And you see, on the next level. Where am I? I don't have the right screen selected. So there are, I believe 5 I have it set at right now. There are 5 AI players playing this game as well. So those players that you see that are just constantly look like they're traveling a predetermined path, those are the AI players. They're running the Pathfinder code, except they have a little bit of extra logic to smooth out the corners. You can't really tell it on this map, but they have a little extra logic to be able to take diagonal paths without getting stuck on walls. So they have a little bit of extra logic, but they're running BFS and finding their way to that goal. And you can notice that mostly on this one, where we have the start and then an end with a maze-like path where there's one way to get to the goal. Even if there were multiple ways, they are running the BFS, the full Pathfinder solution. So they would be able to get through even if there were multiple paths, they would take the fastest one. Okay, so let's start talking about how to build this thing. Let's talk about the architecture of this game, and we can start tweaking things with the architecture and see what changes we get. Let me go to possibly our last slide deck of the semester. I might not have any more slides after this one. Certainly not next week, and possibly not on Friday. So this is 116. Damn it, the description. I try to remember each time, but get my syntax wrong. We're just gonna have the wrong title on this one. I'm not restarting the stream because then we'd be splicing videos together. All right, so next level, please. You have to beat the base to get to the next level, and that is the last level. You're about to wrap around back to the first one. Made this one pretty hard to cheat on. It's possible though. So the enemy base is going to change colors until it gets completely dark, and once it's completely destroyed and blown up, that's when you go to the next level. This is the last level, so it's going to wrap around back to the first one, which the AI take care of the first one really quick, so you actually didn't get to see it. The first one is just a really simple straight shot to the base. So let me go through some slides and explain how this thing works, because there's, of course, a lot of moving pieces. We'll likely talk about this Friday as well. I'll go through these slides. I don't have too many slides. And then we'll click around in some code and see how all everything comes together to be able to build this thing. So here's the top level architecture of this, minus the AI. We'll talk about the AI when we get to the code. But we have the web front end that you're seeing. That's the HTML and JavaScript. No CSS for this one. And that's connecting via HTTP and WebSockets to an Nginx web server using the same infrastructure we're using for the project contribution projects. We're connecting to an Nginx web server, and that web server is forwarding all the WebSocket connection. Damn it, I didn't update the name of this, but to a tower server, a class I named tower server. So let's start picking this apart one at a time and talk about how this thing works and some of the implications of the architecture here. So one thing, I don't think this made it to my slides, but this works off of a very a thin client. I don't know if that technically fits this description, but in spirit, this is a thin client. At the very least, in spirit, this is a thin client where your front end isn't actually doing much of anything. It's grabbing your key states. So whatever keys you have pressed down, it's capturing those and sending those to the server. And then it's getting the game state from the server, the full state of the game, and then displaying that in your browser. So the front end here, in the context of MVC, the front end has the entire view and part of the controller. So it's processing those key states and then sending those to the server as a JSON string, and then the server does some more of the controller part, and then communicates with the model and gets the actual action happening. The whole model, the entire model, is on the server. So this one is tough, as pointed out. It's tough to cheat at this one. You can't just set your location, set your position, set your velocity. You don't have access to any of those things. The only things you can change are the key states. You could write your own bot to navigate the levels and to be able to dodge, actually add some dodge functionality to dodge the balls come from the towers. You could add that and just send the key states based on your bot's determination. But there's really no other way to cheat because all the logic is happening in Scala on my server where you don't have access to it. So the front end renders the game and captures the key states. Then we have an Nginx server, which is hosting the front end. So Nginx is going to send the HTTP and the JavaScript. If this is an HTTP request, Nginx says, I got this, don't worry about it. It does a lot of caching for us, a lot of optimizations. Nginx is very efficient at hosting static files that don't change, content that doesn't change. The HTML and JavaScript files don't change. They're files. Nginx is great at that. Nginx is just going to send those static files directly. If the request is a WebSocket connection, Nginx is going to forward that. It's going to serve as a reverse proxy server and forward that to our tower server, which is a WebSocket server. I know the slides are going to say TCP socket server. When I did, that's the biggest change I had to make to this game to make it work for the current version of the course is 2 semesters ago, 116, we taught TCP sockets. I cut it from the course because it was just a bit much and wasn't really improving education, in my opinion. So I cut it from the course. But this used to be a Python web server, and then make a TCP connection to a Scala backend. It was a bit much. But so it's going to forward the WebSocket connections, and the WebSocket server is going to listen for 3 different events a connected event, disconnected event to add a player or remove a player, and the key states, which are the states of each key, up, down, left, right, what's being held down, and then process those key states to be able to get the proper velocity, the proper location, or the proper direction that this player is intending to travel in. The web server is also responsible for broadcasting the game state to all users. So this server is going to broadcast over every WebSocket connection, which is going to go through Nginx, and send that game state to every user. And since the front end has no logic involved, it doesn't know the velocity of any of these, any object that's on this screen. It doesn't know anything about how these things are supposed to behave, how towers are supposed to shoot, how AI are supposed to path. Doesn't know anything about any of that. So we have to get the game state often. And if we look, and this is kind of an extreme of a setup. Did I have that? Apparently I deleted that first slide. Or maybe that's in a different slide deck. But I should give my disclaimer that this is just one way to set things up. And this is an extreme case of pushing everything to the server. All the logic is on the server and the client's a thin client. That is a very extreme example of how to set things up. So I'll give my disclaimer. This is just one way to do things. This isn't necessarily the way that you do things. So I just want to make sure that's out there. There are trade-offs to everything, of course. But if we look at the WebSocket connections, this just looks similar to the clicker game, except we're running at 30 frames per second now. So you're getting the entire game state, the location of every tower, the entire map, the location of every player, and the location of every projectile in one giant JSON string 30 times per second. So if you run this, if you have this running in your browser for a while, you might hear your fan start to spin up a little bit. Because we do have a lot of communication, a lot of processing that's happening. This isn't really optimized. I could just have the dynamic objects sent every time, and not all the static objects as well. But you can see all the communication. If you open up your console, you can see 30 times per second you're getting a WebSocket message with the whole game state. So that's how we get this fluid motion, even though the front end only knows how to render a game state. It takes a game state and displays it. That's all it does. But with frequent updates, we actually get some smooth looking animations, but it's just 30 times a second updating the display. Just how, that's how we consume video content anyway. It's just usually not a network involved like that, sending every single frame. So 3 events that we're going to react to: connected, disconnected, and key states. And then broadcast that state to every player 30 times per second. So if 100 players are connected, my server is broadcasting the whole game state to 100 separate WebSockets 30 times a second. Only 30. I mean, I could set it to 60. It's just going to use up more resources. Which one am I looking at? So I'm at 63% CPU as it is. So, because this is fairly inefficient. So I'm using up a lot of CPU as it is to do all this processing. So yeah, I could do 60, but I'm going to use up more processing power. And possibly more importantly, I'm going to burn up all your CPUs as you're running the game in the browser. That's a lot of processing that's being done in the browser. So yeah, only 30. If it wasn't networked, if I wasn't going to this extreme in architecture and doing all the processing on the server and sending the game state, if I had the front end understand some physics and just send the velocities every once in a while, and the velocities as they change, then 60 frames per second would be no big deal at all. Yeah, ray trace. There's all kinds of stuff we could add if we want to. This game could be optimized. It's not meant to be optimized. It's just meant to show the concepts, how you can build something like this using the things that you know. We're not talking about optimization. That's the next 3 years of your career. It's optimization of your educational career. You'll learn about all kinds of stuff. We don't need to cram it all into your heads. Year 1. So everything else, all of this in this green box is going to run in Scala. This is one actor system, and all these boxes are going to be actors in that system. And this is what's going to run the game itself. So we're going to run this server. It's going to start up the one instance of the game. We only have one instance of the game running. But notice, since this is an actor system, we could have multiple instances of the game running on a single server. So if we wanted to have like a lobby and wanted to have, you can get your raid of 10 people together and go start attacking bases. We could set that up and then just have multiple game actors for each group of players, for each kind of room, each lobby or whatever. And then the socket server would only send to those players that game state according to their game. And then when they get key states, only send it to their game. So somewhere in between this, a single instance of the game actor, and Clicker, where every single player gets their own game actor, we can do something in the middle, combine both of those ideas. So if we wanted to have that, lobbies and then forming games and creating games, that's kind of trivial in an actor system. We're already set up to be able to do that. Just spin up a few more actors and nothing else is affected. PC froze for a minute playing the game. If you open the browser console and go into, like if you do what I did here, this takes a long time to load. If you haven't opened it, because it's loading this entire history of all of these messages that have been sent. It's a lot of text. It's a lot of characters to display. 30 times the number of seconds you've had it open. If you open up that and go to messages, it takes a while to load. So I'm guessing that's what you did to have it freeze for a bit. So we're going to start the server, and the server is going to set up the rest of the actor system. It's actually only going to create the game actor. Then the game actor creates these other actors. So this server is, of course, going to listen for WebSocket connections on port 8080, as we're used to. And it's going to create that game actor. It's add that to the actor system as it's being created. And then it's going to listen over the WebSocket for the key states of the user. It's going to listen for every action that each player is making. It's going to remember which player they're associated with in the game, their username, their player name, and it's going to say to the game, hey, game, you should move this player because they just sent me these key states, they sent me this action that they want to take. So it's going to send that to the game actor and say, this player is intending to move diagonally up and to the right. It's going to send that to the game actor. Game actor is going to handle the physics after that. So it's responsible. It's acting as a controller here. It's going to receive WebSocket messages, and it's going to convert those into actor messages to send to the game actor class. The game actor is only speaking actor messages. The client is only going to speak over WebSocket messages. So the server is going to do that conversion and look up for this WebSocket, who's the player associated with this WebSocket, and send that information to the game actor. Hey, game actor, I got this player. They want to move. The game actor is also going to send the game state and then server broadcast. I mentioned that earlier, though. So the game actor, it's going to receive these actor messages concurrently from the server saying, hey, this player is intending to move in this direction like this. This player is intending to move. And the game actor is going to receive those messages, of course, concurrently, asynchronously. And the game actor is going to have an update loop for the physics engine. 30 times per second, it's going to update the physics. It's going to call the physics engine code from that homework 1, if you chose physics engine. And it's going to call update world 30 times every second on an infinite loop. Our core update loop for the game, all that physics is updating. It's also going to 30 times per second send the current state of the game to the TCP socket server to broadcast that over the WebSockets, broadcast that current game state to all the connected players. And that's a variable, of course. We could change that to 10 FPS, 60 FPS, whatever we want to change it to. Just performance and resources trade-off at that point. But this game can handle 60 frames per second the way I have it set up. It's just more resources. So the game itself, we do have some MVC set up, kind of different layers of MVC set up here. The game itself doesn't know or care that it's part of an actor system. We still have that set up. We can look at this closer when we get to the code. But the game itself is a model. I have a game class that acts as a model, has its API that the game actor can call. And then the game is going to handle physics and all kinds of other stuff without caring about the actor system. So the game actor gets these actor messages, which are still platform dependent, language dependent, dependent on a lot of library dependent on a lot of things. So we're going to translate those into method calls of our game, which are much more general. We're going to call those methods in the game and then have the game react however it needs to react when it receives those API calls. So the actor is controlling it, converting those actor messages. We have a few layers to the controller. Capture user inputs, send them to the server, forward them to the WebSocket server, those WebSocket messages, convert those to actor messages, and then convert those to API calls of the game itself. So we have a few layers of data transmission, data processing, before we actually get to the API call. But we want to write the game in isolation without caring about the rest of the details. If we're trying to keep all of those details in our head all at the same time to build one feature, we're going to get bogged down. It's going to be hard to concentrate. But when we're writing the game class, we don't think about any of the networking. We just expose an API. Oh yeah, 2 servers. So this is a WebSocket server listening only for WebSocket connections. And it's internal to the to this server. I guess the word server is pretty overloaded, but it's internal to this machine, and then Nginx is going to be the server listening for outside connections. So these connections are over the internet, and then these connections are internal to my machine. So I have one server listening for outside connections, and then it's going to act as a proxy server to forward only the WebSocket connections to this WebSocket server. I know it says TCP socket server. I forgot to update the name of this one. But it's going to talk to this WebSocket server, and the WebSocket server processes those messages and communicates to the actor system. So a lot of moving parts. Hopefully you can start seeing how things are coming together here, how different concepts of the course work together to build one piece of software, one application, an MMO in this case. And then the tower actors. So is each WebSocket an event listener? Not each WebSocket, but each type of thing we're listening for. So we have a listener for connect, disconnect, and key states. So we have 3 listeners on this server listening for different types of WebSocket events: connect, disconnect, and sending the key state message. So when the game actor spins up, it's going to create the actors for each tower as well. So for each level, each tower gets its own actor. So each tower is working independently of each other. So each tower is actually, I don't want to say thinking, but each tower's logic is happening concurrently. So each tower can work on its own without interfering, without blocking other parts of the process. And this is an important part of a demo I'll show towards the end of lecture. That even if a tower, say, so these towers are actually running the genetic algorithm. Even if that genetic algorithm is very inefficient, and that tower takes more than 1/30 of a second to compute, we don't want that tower blocking the updates that are sent to the users. We still want this game running in 30 FPS, even if the towers want to take up a lot of processing time and take forever to figure out where to shoot. And I'll demo that. I'll show that and I'll chew up my CPU on the server, and we'll hopefully be able to see the game still running at 30 FPS, unless the towers just tank all the resources of my droplet, which they might. I mean, it might happen, but if all goes right, we should see at least some aspect of what we want to see. So, we're already at the end of the slides. So we can discuss this, and I'll go through the code and show how this can work. But how to add AI to this game? We do have AI in the Towers game that's live right now. That's working similar to the Tower actors. Is we create a separate actor for each AI, and I actually have an AI controller actor, which then controls all of the AI actors and maintains all the AI actors, so the game actor doesn't have to really think about it. It just creates the AI actor. The AI actor then sends messages to the game actor in the same format that the socket server is sending messages to the game actor. So one thing you might ask is, why do we have so many layers here? Why are we sending WebSocket messages and then converting them to actor messages and then converting them to API calls to the game class? And there are reasons for that. There's some good, some bad. For example, why doesn't the the Tower server, which it's called now, just receive the WebSocket messages and convert those to calls to the game class API directly? And then we can have this server absorb the game actor class, whatever it's responsible for, and then have all of that work done there. That skips the step of converting from WebSocket messages to actor messages to API calls. We can do that and kind of simplify something, but what we have here is called separation of concerns. This server, this WebSocket server, should only be concerned about WebSocket stuff. It shouldn't be concerned about game logic or calling the game API. We don't want this server to have to worry about that. So when we call encapsulation, good call. Encapsulation and separation of concerns, when we're thinking at this kind of diagram level, we want to hide the details. At both of those, the goal is to hide the details and expose API. So this has an API of saying, I listen for WebSocket messages of these types, and I receive actor messages of these types. Everything internal, we don't care about. But once we start eliminating these interfaces and combining things, we have less. But first, we have more to think about. If this is all one class, we have a lot to think about of what that class has to do. There's a lot more it's responsible for. So it's harder to write that class, where if we're writing this class, we only think, how do I convert to and from WebSocket messages to actor messages? It's really all this thing's responsible for. The game actor, how do I get actor messages and convert them to calls to the game class? It's all it's responsible for. A tower actor, it's only responsible for getting actor messages and calling the API for the tower class. There's each component has one thing that it's responsible for, and it's hidden. The details are hidden to the outside world unless you're developing that particular piece of the project. So if we combine those, we have a class that's tougher to write, but also it's tougher to expand. Another benefit we get from separating things like this and encapsulating them is to add an AI. So first, for a human player, we're getting the key states in the WebSocket server. The socket server is converting the key states into messages to the game actor class, which tell the game actor class, hey, this username intends to move in this direction. Now when we want to add AI, we use this same interface. We have an AI actor, which is going to do the same things that the socket server does, but instead of listening for WebSocket connections from human players over the internet, instead it's going to create game actors, which are AI actors, which are going to compute for themselves. They're going to get the game state, read the game state, just like you do with your eyeballs over here. They're going to read the state of the game, run some computations and figure out what direction they intend to move in. We're going to give each one of those AI a username, so the game actor just sees them as any other user, human or AI. The game actor doesn't care if they're human or AI. We're just going to send messages saying username this intends to move in this direction. It happened to be generated by an AI, but the game actor doesn't care. It just sees username wants to go in this direction. So we separate what the human players and the AI players, but we use the same actor messages that we're sending to the game actor class. We have the same interface, the same interactions with the game actor class. So the game actor class, nice and versatile. The way it works, it doesn't have to care if those are human or AI players. And let's see some demo of this. So our stuff's running fine. And let's, we'll go through the, you know what, let's go through the code now, right? I think that makes more sense. We'll watch the game while we're going through some code. So this repo's private. There are some pretty obvious issues with making this public. Resize this. As we'll see, if it's not clear yet from what I said earlier, there are solutions to 3 different homeworks in this code. So making it public just doesn't... I'm thinking of ways, because I do want to make this public. I'd like this, or at least some other MMO, which is going to have a lot of the same logic. I would like to have that be open source and available to the class. 1, for you to study and just use as an example. But 2, if we can use that for one of the open-ended projects. If you can contribute to this, if you could make a new level as your project contribution, I think that'd be pretty neat. And we could have a cooler app and more fun stuff to play on the game. So I'd like to do that, but I got to get around that, having 3 homework solutions out there. I have ideas, but we'll figure it out. The Nginx, Dockerfile, Docker Compose, POM, all these are the same of the other examples that we saw. We want to focus on the actual code running this thing. So let's start with Tower Server, which was labeled TCP Socket Server in the diagrams. Let's look at this class, and there are a few things that we want to do here. Actually, I don't think I'm using these data structures. I don't think I needed these. I needed the socket client to actor. No, I didn't need any of these. I don't use these. I don't know why these are here. I ended up not using these at all. But the rest of this setup is what we expect. We have a connect and disconnect listener and listening for the key states. Those are the 3 WebSocket events that we're reacting to, and these are the setups for those. And we'll see the listeners down below after we look at the rest of this. We also have the actor side of this, reacting to the actor system. As an actor, this can get a request a request to request that it's getting every 60th of a second or 30th of a second send game state message. It's getting that message and then forwarding that to the game actor. We're sending the game actor the send game state message, which is a request. Hey, can you send me the current state of the game? And then when it responds with the game state, we're broadcasting that to every web socket. On a connection, we're going to add that player to the game using their sockets ID. That's how I get around using those data structures. On disconnect, remove them from the game. So if I have So if I have a character and then I disconnect the WebSocket, that character is going to disappear immediately. So I'm removing them from the game. So I have 2 actor message types that I'm sending to the game actor. add player and remove player. Those are my first two actor messages that I can send to the game actor. That's part of its API that it supports. It supports add player, remove player messages, and as we'll see later, move player and stop player. When I get the key state message, this is a little more involved. I'm going to read the key. Oh, I meant to clean this up a little bit. It's a little verbose here. But I'm going to pull the state of each key from the key states message. And you can look in your JavaScript to see how this is generated. It's looking at your either arrows or WASD. You can use either for this game. You can't see me touching the keyboard, so I don't know why I showed that in the browser. But I was using WASD and arrows to do that. You can use either one. So it's going to check the state of each one. You'll see whether it's up or down. Each time you change states, it's going to send a new WebSocket message of type key states to say, hey, the states of the keys for this user have changed. Update accordingly. So I'm going to grab all the key states and check the X and Y direction. Depending on which keys are up and which keys are down, I'm going to decide which of the 8 directions that you want to move in. I'm going to send the move player message to the game actor, or if all keys are up and X and Y are 0, I'm going to send the stop player message saying, hey, this player is not moving anymore. They let up all their keys. Send the stop player message to them. Then I'm setting up the tower server itself. The AI, they're going to run their path finding at 10 frames per second, and I'm going to update the game and send the game state at 30 frames per second. So this is updating all the physics, and then kind of offset from that, I'm going to update the game states and broadcast game states to all the WebSockets. This first time is the delay, so I'm going to wait 16 milliseconds and then start firing this off every 32 milliseconds, and then 32 milliseconds to wait, and then every 32 milliseconds I'm going to send this state. So I have these out of sync. I'm going to update the game and then send the game state message in between updates, and then update again, then game state message. So I have those staggered a little bit so I can get the updated game state message. And hopefully update game takes less than a 60th of a second to compute, and then by the time that send game state message comes, the game state is updated. Which isn't guaranteed. It might not always be happening, but that's a setup that we have. What part did I say I was going to go back to? Oh, I guess the listeners. So that's all the server. I think the AI at the top are broken. I mean, those are humans. I mean, they might be broken, but that's not for me to judge. That's just a little party they got going on up there, it looks like. There are 5 AI characters, and we can see those 5 AI. Once they die, they go back to the base and respawn. We can see there's 5 of them. Oh, the AI are fine. It's the humans I'm concerned about. But to each their own. So, screw it. I'm going to join the party even. So, I have my window resized too much here. So that's the server itself. Ooh, yeah, this is fun. So that's the server itself. Let's talk about the oops, not the tower actor. The game actor. So the game actor is doing similar stuff. It's doing processing, game level processing, but mostly just converting actor messages into API calls. So this is still part of the controller, just controlling the model itself. So for this, we're going to set up the level, just read which level we're on, and then appropriately advance levels as we're moving through. So when we update the game, for example, I want to check at this level, no pun intended there, but at the actor stage of this app, I'm going to check, is the base gone? If so, let's move on to the next level. When we get these add, remove, move, and stop player messages, all we're doing is forwarding those to the game that we're initializing in this actor. When a game actor is created, we're creating a game class, which is going to control all the actual logic of the game. and then we're forwarding messages to that game, to that game when we get those messages. Now, at this point, add, remove, move, and stop. These could either be coming from a WebSocket connection from a human player or from an AI actor controlling a team of AI players. It doesn't matter what these are, where these are coming from, or who's on the other side. We just know when we receive actor messages of these types, we react accordingly. And yeah, seriously, where's the social distancing here? Get away. So one thing I removed when I changed the stuff, I'll probably have to add it back in, depending on what happens here. But I removed my check to make sure there was only one player, one actor, or sorry, rather one WebSocket connection per IP address. Hey, you're gonna get me sick, dude. The hospitals are overloaded. I just have to go somewhere where nobody's gonna bug me. Oops. Not like that. Oops. Not like that. Getting owned by my own game. Yeah, spelling high is fine, but I've had less savory stuff where I had to add that IP check. So we don't care where these messages are coming from, as long as they're being forwarded to the game appropriately. What's the next thing I want to talk about? I guess the game itself, and then I'll talk about towers. So the game itself, we're going to have a world for our physics engine. We're going to have all of our static and dynamic objects. All the physics are going to be applied here. Each wall is a static object with collision detection. All the good physics engine stuff. Add and remove players, updating data structures, nothing too exciting there. Setting up the physics engine. This is actually using an old version of the physics engine homework. And actually maybe that's how I can get away with releasing this code, is I am using previous versions of each homework assignment. They're not the versions that are being offered currently. So I might just be able to release this as is. Possibly, potentially. And you're going to get me sick. I do want to hide. Whoa. So it handles all that good stuff. The base taking damage when a player is close enough to the base, all that good stuff that's happening there, and a bunch of JSON generating that game state and shipping that out whenever somebody asks for the state of the game, which our game actor is going to ask for. Whenever we want the game state, we're going to ask the game, hey, give me your state, so I can send that in a message to whoever is asking for that state. And then the game uses the physics engine code, a little bit different. Again, it's a previous version of the assignment, so a little bit different, but same idea, collision detection, and then handling those collisions. The towers, so a tower actor doesn't really respond to any messages coming in. It has the fire message and the game state message, but it's kind of initiating both of those. The fire message is only sent by towers themselves, and it sends itself fire messages. The game itself doesn't determine when a tower should fire. So, and we're going to request the game state from the game, and then when we get the game state back from the game, that's when we're going to initiate a fire. We're going to update our game state so we have the latest information. Tell the tower is going to tell itself to fire, and then it's going to call this aim fire method, which is the aimbot code, which is running the genetic algorithm. So it's going to take that game state, parse it all, figure out everything, all about its location, and it's finding its closest target, all kinds of logic in there to be able to figure out who it's targeting, and then use aimbot to figure out where to fire. Once it does, it's going to tell the game actor to add a projectile to its game. So the game is going to add a new dynamic object with the location of this tower and the velocity determined by the aimbot. We're also using the Z direction. Even though this looks like a 2D game, we are using some 3D physics here. So we are using the full 3D physics engine, and we're using the Z position, location, and velocity to determine when one of those projectiles should disappear. So we're using a height, I believe a height of 3 units for what it's worth, and then this ball actually fires in a parabola, and when it hits the ground, that's when it's going to be removed from the game. So we do use some 3D logic from our physics engine to determine, I don't have like a set distance or anything. Towers have a specific height and a launching velocity, and that determines when that projectile hits the ground. Then we assume players have infinite height, or at least 3 units of height for those. Then we could add arcs. We could add all kinds of 3D stuff here. One thing I would like to add to this, or maybe a student can add it, is a first-person view, so you can actually see all of that and look at how it's all rendered. We do have a 3D game world being shipped in the message. Actually, I don't know if all of the 3D stuff is shipped. It might be, but we're shipping all that information in the game state. It's up to the front end to render that however it wants. So if the front end just happens to render that in a first-person view instead of a top-down view, it's welcome to do that. That's something that we have the power and the technology to do. So the tower works with a dodgeball tower. It's technically a dodgeball game, so it's not violent, don't worry. And here's where we have the height of a dodgeball tower. This is what the model that's being controlled by the tower actors. We have a height of the tower to figure out, which is going to determine the range of a projectile. We have the sight range, so a tower will not fire unless you're within 5 units of that tower. If no player or AI, like this tower over here, no one's within 5 units of this tower, it's not going to fire because nothing's in its sight range. The projectile velocity, of course. And then all the stuff to set up the genetic algorithm, the cost fitness functions in this case for this iteration, before I move to cost functions. A bunch of physics stuff. We've talked about that earlier in the semester. In the genetic algorithm, this, again, a previous version of the assignment. It was a fitness function instead of a cost function, and they were allowed to use var at this point. So this solution, I could switch it over to my other solution and do a cost function switch the cost function instead of fitness function, retrofit this thing. But this is a solution to a different genetic algorithm to be able to fit in what this iteration of the assignment was. So without going through, the next thing will be the AI. I can talk about it in Q&A, and I'll probably pick that up in Friday's lecture. But the one thing I do want to show before we cut the lecture portion today is I want to go into the code for this. I'm going to restart the server, so we'll go back to level 1. But I want to change some of the code here and get what we promised before. And this will take a little while to rebuild the thing. Genetic algorithm. What I want to do is increase my population size and increase my number of generations. Let's go 100 and 100. To get my, so I have that at, I think it was 5 and 5, right? I want to get a lot more inefficiency. Let me make sure this is running before I start talking. So I want to get a lot more inefficiency in my towers, in my aiming for that. So instead of having a really efficient algorithm, I'm going to simulate my algorithm being much less efficient just by adding to the generation size and the number of generations. And what we should see is the towers being very slow, very sluggish, as they're taking a long time to think about where they're going to fire. But we should still get a nice smooth running game at 30 frames per second, because those towers are taking up a lot of time, but they're doing it concurrently. So that tower doesn't monopolize our CPU, because we're able to run everything else in parallel, not in parallel, but concurrently with with those towers. So those towers, they're taking a lot of time to do their stuff, but at the same time, all of our other game logic are sending the game states, producing that JSON string. All of those should not be hindered. Now again, it's always possible this goes wrong because those towers are going to really take up my CPU. So I might just start maxing out my CPU with, a bunch of, 6 towers for this level. 6 towers all running a very expensive, man, I lost my words. A very expensive genetic algorithm, 30 times per second. So if that takes any longer than 32 milliseconds, these things are constantly processing some fire. Well, that's not necessarily true. But these things are constantly thinking and computing where to fire if they take longer than 32 seconds.